Hello, welcome to the Automotive Embedded series. So, every time when you turn off your car, dozen of tiny settings get saved somewhere. Your seat position, your last odometer reading, fault codes, and calibration data. For example, none of that lives in RAM because RAM forgets everything the instant power drops. It has to live in some kind of persistent memory. So today we are going to talk about flash memory. But here's the problem. Flash memory wasn't designed for this. It wasn't designed to be updated constantly for decades without ever corrupting a single byte, even if someone yanks the battery mid-write. So today we are going to have a look how automotive engineers solve that problem and why the solution looks nothing like a flash storage in your phone or a laptop. So why the flash is so hard to write? Quick refresher on how flash works, physically works. Data is stored in cells grouped into pages. Pages are grouped into blocks. You can write to an empty page directly, but you cannot flip a bit from 0 back to 1 with a simple write. You have to erase the entire block first, and erasing is slow, high wear operation. And when I'm talking about block, it's not like some 1 or 2 bytes. A logical erase block could be up to 512 bytes. So think how much block you have to erase before you are writing back. This creates two problems for something like a car. You cannot just overwrite a value in place the way you do with like RAM, or every erase cycle physically wears down the cell. So every cell has a limited number of writes. You cannot write them infinitely. Like for example, every block, let's say, have 100,000 writes and then it get corrupted. So Flash has, that's what I'm telling you, Flash has finite number of erase cycle before it's become unreliable. For a car that might be in service for 15 to 20 years, knife flash write would wear out of memory long before the car is retired. Now, you might ask me a question. Why don't we just use a normal file system? Why we have to use like something called a persistent memory? Consumers will deal with this using wear leveling like FAT or extension 4 or a flash transition layer. Automotive system don't use any of that. There is no OS file leveling system, no directory structure, nothing resembling Y on your laptop SSD. So when you develop a ECU or a software for a MCU in a car, like the multi controller, you use the basic operating system like free RTOS, right? Which just provide you with tasking and runnables and all those things. They don't provide you with a file system. So you cannot just use an automotive MCU like you use a CPU in your laptop. So what does actually happens here? Instead, the layer that talks to flash in an automotive ECU is very small and a very deterministic behavior or a deterministic driver, often something inherent from EPROM emulation. If you're interested in EPROM, we can also talk about EPROM in a different video. Just put a comment. The reason is simple. Automotive software has to behave predictably within microsecond, has to be certifiable to a safety standard, and cannot depend on a general purpose file system, unpredictable timing, or its assumption about power always being available. This is where AUTOSAR NvM stacks comes in. It's a standardized layer that manages how the data gets written into Flash in a very safe and predictable and long-lived manner. Let's approach few of the methods which can be used for wear leveling. And the one thing which we called is called two bank trick. Here's a core idea that makes this all work. Instead of one region of flash, automotive system typically uses two banks. Walk like something if you want to understand. When the ECU wants to save a piece of data, it doesn't erase and overwrite in the same spot. It writes to the new version to a new fresh location in an active bank. Once that bank started filling up, the system copies all the valid data over the second bank and the first bank get erased in the background. So basically the cons of this approach also is that you're dividing your whole flash area um, into two parts. One is called like A and one is called B. A is active, B is standby. And when you write to A and A is about to get filled, then you copy all the data to B and start writing B. And similarly, A A will become standby in this case and it will get erased. Similarly, what you are seeing currently in your picture, like B is a standby which is getting erased in the background, and A is currently active which is getting written. Why does it matter, right? Because everything what we do should matter in some way, right? So the first point is power loss safety. If the car loses power mid-ride, the old copy of data still is intact in other bank. You never end up with half written corrupted value. So what you're providing is consistency and availability of the data. Wear leveling. Writes get spread across the whole flash region instead of hammering the same cells over and over. So now you're not just writing one cell, you're writing the data into multiple cells. So the life cycle of your flash or the life cycle of a particular block is longer than whatever the erase cycle of your flash is. Predictable garbage collection. The swap and erase process is what trigger garbage collection, and it happens in a controlled way rather than a randomly stalling the system. This is effectively how EEPROM emulation has worked for years and why it many automotive flash drivers are built on top of that lineage rather than from scratch flash controllers. Now, a natural question. If you're writing of to flash this often, how long does it actually last? Right? This is the question you want to ask to me as well. So, automotive flash cells are typically rated over tens of thousands to over 100,000 erase cycle, depending on the memory technology. Combined with the two bank rotation, wear leveling is spread evenly, and the real world deterministic automotive write patterns land in the range of almost 20 to 30 plus years of service life, which comfortably outlies the vehicle itself in the like in the majority of the cases. Now the caveat. This assumes the normal usage pattern. A system that is misconfigured to write far more often than it needs, say logging something every few milliseconds instead of only meaningful changes, can burn through the lifetime budget much faster. This is actually one of the most common real world bugs as well, and every time there is a good or a better solution for it. So, over aggressive write frequency quietly eating years of the flash usable life. And sometimes this has to be solved at a software layer and many different components or many different types of storage system has their own solution. Why this matter beyond the car? The same two bank wear conscious pattern shows up anywhere in the embedded system needs durability without a full file system. Industrial controllers, medical devices, even some IoT firmware. Once you understand the automotive version, you will recognize the same shape everywhere. Now we are basically ending to our close. If you work anywhere near AUTOSAR embedded flash, you would probably test some of the version of the system without necessarily seeing the full picture end to end. Next time in this series, we will look actually which triggers the garbage collection under the hood and what happens if it doesn't run it enough. If this was useful, please subscribe more. The series is upcoming. Thank you so much for watching this video and have a nice day.